Okay, so x plus 1 is also a factor. X minus 1 is a root. So we've got two negative roots here. Remember, this is a positive 1, negative 2, positive 3, and negative 1. Two negatives, two positives. So that means there still might be a third number. For the positives, there might even be 3 more positive numbers. But at least we know we've gotten 3 from 9 down to 2 now. And so we can replace all of this with 1, negative 1, 1, negative 1. Seven to 6, 6 to 5, 5 to 4, 4 to 3. So now we're on 3 to 2. Once we get to the quadratic 2, then we can start seeing if there's a rational number that'll work. But right now, we've got to try something different and take care of this number here. Well, looks like 1 will work again. 1 times 1 is 1. 1 minus 1 is 0, 0, 1, 1. Okay. Looks like it looks like 1 is still a value, which is exactly the same as that first one right up there. That's multiplicity. That means you've got a certain factor that's being used multiple times. But what does this leave with now? Well, it's the x minus 1 times x plus 2 times x plus 1 times x minus 3 times x minus 1, and then that leaves us with x squared, no x, plus 1, and this is where we try and solve the rational equations, the rational factors that might exist. Okay, so now from here we can take this quadratic formula of sorts, x squared with 0 x's and positive 1, we can set it to 0 and then subtract 1 from both sides to give us x squared is equal to negative 1. Take the square root of both sides, and you get x is equal to, you guessed it, I. But you can't just have one I. You can never have a single I in a polynomial. It's got to be a conjugate pair. So that also means we've got a negative I as one of our non-real roots. So that means we've got 2 non-reals, we've got 2 negatives, and we've got 1, 2, and a third one which we haven't found of the positive numbers. So this was the combination we came up with for this problem. Okay, this next part we're going to cover deals with the intermediate value theorem, which states that if there is a number at point A on a graph, and then you've got another point at point B, and you've got both of them plugged into the same equation, your polynomial, then that means that there is almost always going to be a point that's going to be a root between P of A and P of B. So P of X is going to be equal to all the values of PA and PB. The best way to show you this would be to use a graphing calculator, which I have right here. Now, let's say that you wanted to check a polynomial to see where the zeros are, just using graphing calculator. Well, here is an example from Gustafson and Frisk's book. 2x squared plus x minus 3. And they ask you to prove that there's a point where there's a root between P of A, which is going to be -2, so we're going to go into our window and set our minimum to -2, and point B, which is going to be 1. So I've set up the x max and the x minimum to show that the graph's going to be showing us between -2 and 1 on the graph. And as you can see, it's drawing. There is indeed one root between the two numbers. In fact, there's almost 2 there. And this is because all the points between P of A and P of B will become part of P of X. And that means that somewhere between those two numbers, there's probably going to be a root there. Or there's always going to be a root there.